Okay, so we were discussing about the Z transform. So now today we will see the properties of Z transform. Okay, so now what are all the properties of Z transform? Okay, properties of Z transform. So what are all the properties are there? So first one, so as like in your Fourier representation, linearity property, and then you have time shifting. Okay, time shifting property, and similarly you have the scaling property. So this scaling, actually we'll call it as scaling in Z domain, because when you scale the factor, or if you multiply the factor in time domain, that correspondingly, so it will scale in Z domain. So that's why we'll call it as scaling in Z domain. And also we can have time expansion. So expansion in the sense we'll just pad the zeros in time domain, so that will leads to the time expansion. So that will give the corresponding Z transform, which will improve the spectral efficiency. So that will the property which will be having time expansion. And we'll have differentiation in Z domain. Okay, differentiation in Z domain. And also we have the property of the convolution that we have already seen in Fourier representation also. Okay, so differentiation also we have seen. And another properties which is called as accumulation. Okay, accumulation. And one more important property which is called as initial value theorem. Okay, initial value theorem and final value theorem. Okay, so these are all the some of the important properties of the Z transform. So now we will go and see what are this linear property and what is this time shifting and all. So we will go and see these properties, and we will prove the properties also. Okay, so these are all the some of the properties of Z transform. So now we will come to first property, which is called as the linearity property. Okay, the first one is linearity. So what is meant by linearity? So now if you have a signal x of n, okay, which is having a Z transform, corresponding Z transform x of z, okay, so then if you have the signal, two signals, that is x1 of n and x2 of n. Okay, say for example, if you have two signals x1 and x2, okay, so if you have the two signals x1 of n and x2 of n, okay, so now the corresponding Z transform will be having x1 of z and x2 of z. Okay, so then what this linearity property says that, so if you have the addition x1 of n plus x2 of n, okay, in the time domain, that is in the discrete time domain, so that corresponding Z transform which will give x1 of z plus x2 of z. Okay, and also the scaling property. So if you scale the corresponding x1 of n by a and corresponding x2 of n by b, so then the corresponding scaling factors will also appear. So if it satisfies, okay, if the two signals satisfies the scaling as well as the additivity property, so then that system, that Z transform, which will be possess linearity property. Okay, so then we will prove that. So if you have the x of n, which is corresponding Z transform x of z, so then we will take y of n, which is equal to a into x1 of n plus b into x2 of n. So now this corresponding y of z, the Z transform of this y of z, which will be given by a into x1 of z plus b into x2 of z. Okay, So now we will prove that. So we know that the equation for the z transform, which is equal to y of z summation n equal to minus infinity to plus infinity y of n into z power minus n. So now we know y of n. So in terms of the discrete time domain signal, you substitute that, so then we will get the z transform. So you substitute that and we will get, so y of z, so which is nothing but the summation n equal to minus infinity to plus infinity. So now we will substitute y of n, that is a into x1 of n plus b into x2 of n. Okay, so this multiplied by z power minus n. So now this you multiply the z power minus n to both, and if you split the summation, so you will get it as minus infinity n equal to minus infinity to plus infinity a into x1 of n into z power minus n plus summation n equal to minus infinity to plus infinity b into x2 of n into z power minus n. So now this we can write it as, so you take outside a, so the scaling factor, and this summation with x1 of n into z power minus n, so that we can write it as x1 of z. Okay, and similarly here b take outside the constant, and the summation and x2 of n into z power minus n, we can take it as x2 of z. Okay, so this is the y of z. So if you have the signal which is in time domain, the scaling factor a with the signal x1 of n, and adding to the another signal which is scaling factor b into x2 of n, so then the corresponding z transform will be, so this one a into x1 of z plus b into x2 of z. So then the system which will be, we can set it as, system is set it as linear. Okay, so the z transform, whatever you take the system of that z transform, it will be having linear property. Okay, so this is a proof of that. So how we'll get the linearity property. So this is about the linearity property. So next one, so the second property which will be call it as time shifting. Okay, so now if you have x of n, which is z transform, which is given by x of z. Okay, so now if we shift the signal by the value some value n naught, if you shift the signal in time domain, then its corresponding z transform will be the multiplication factor, that is z power minus n naught. How much you will going to shift in the time domain, so that will be multiplied in z domain, that is z power minus n naught into x of z. So this is the z transform of the time shifted signal. So now we are going to prove this. So now we know the z transform of x of n, so which is equal to n equal to minus infinity to plus infinity x of n, so into z power minus n. So now this time shifted signal we can take it as y of n. Okay, and the corresponding z transform, okay, so y of z, so that will be equal to z power minus n naught into x of z. Okay, so now we can write y of z. So what is y of z? Which is equal to n equal to minus infinity to plus infinity y of n into x z power minus n. So now substitute y of n in terms of the x of the time shifted signal x of n minus n naught. So you will get y of z, which is equal to summation n equal to minus infinity to plus infinity, so x of n minus n naught into z power minus n. So now we can take n minus n naught equal to some variable L and substitute it. So what you will get? Y of z. So if n equal to minus infinity, so you will get L as minus infinity, and it is minus infinity to plus infinity x of L into z power minus n, you can substitute it as L plus n naught. Okay, so now you will get it as, so you can take this the factor z power minus n naught, because the variable is L here. So z power minus n naught you can take outside, So then you will get the summation L equal to minus infinity to plus infinity x of L into z power minus n. So now L is the dummy variable, you can replace L by n, so that will represent the same x of z. So we can write this one as z power minus n naught into x of z. So this is the proof of the whenever you shift that signal in time domain by the value n naught, so the corresponding z transform will be given by the scaling factor z power minus n naught into x of z. Okay, so this is what the time shifting property. Okay, so is it understood? Any doubt? Is it fine? Any doubt? Okay, so now we'll go to the next property, so which will be called it as the scaling property. Scaling in z domain. Okay, scaling in z domain. So now that if we have x of n, which is the corresponding z transform, that is x of z. So now the scaling in z domain means, so x of z by something, some value we can represent here. It is nothing but the scaling. Okay, so some value k I will write it here, x of z. So now what is the corresponding time domain signal? So if we want to scale the value k in z domain, now what is the corresponding signal in time domain? So that we need to know. That is, so we will get, so either we can k or n we can represent, so that will give the scaling in the z domain, so which will be given it as, so I will take here some other factor, or you can write it as z by k, so which is nothing but, so k power n into x of n. So whatever the multiplying factor in time domain, so that will be correspondingly scaled in the z domain. Or you can write it as, so generally we will use alpha power n, k will be used some other notation, so I will use here alpha. Okay, z by alpha, or you can take alpha power n. So now if we have the scaling factor alpha, so in the time domain it is multiplication of alpha power n. So now we will prove this. So we know the this we can take it as y of n. Okay, so then corresponding y of z will be nothing but x of z by alpha, which is scaled version. So now we will take the y of z, so which is nothing but the summation n equal to minus infinity to plus infinity. So we are going to prove y of n into z power minus n. So now y of n we can replace this one, so which is nothing but n equal to minus infinity to plus infinity alpha power n into x of n into z power minus n. So now you combine this alpha power n and z power n, so you will get it as y of z, which is equal to summation n equal to minus infinity to plus infinity, so x of n into, so alpha into z power minus 1 whole power n. So now we have to represent in terms of minus n, so I will write it as alpha power minus 1 into z. Okay, in order to get the y of z, so I will write it as z power minus n and here alpha power minus 1. So now this we can write it as, so n equal to minus infinity to plus infinity x of n into z by alpha power minus n. So now this we can represent it as x of z by alpha. Whatever corresponding z will replace, here it is, if z power minus n is there, we can write it as that x of z or y of z. So here it is the z scaled by the value alpha, so that's why you can write it as this x of z by alpha. Okay, so this is the proof for the scaling in z domain. So now if you want to scale the z domain by a factor alpha, you have to multiply alpha power n factor in the time domain itself. Okay, so this is about the scaling in z domain. Is it understood? It's fine. Okay, any doubt? Okay, so this is again scaling in z domain, it is over. So then we will move into the next property. So so which is time expansion. So that is, if you expand the signal, whatever scaling in Z domain happens, in the similar way time expansion. So you might have remember the time expansion in the sense the basic operation whatever we have, x of at or x of t by a, something like that. So it will shrink the signal and it will expand the signal. So that operation we are using here. If you have the time expansion, so then what is the corresponding Z transform? Okay, so that we'll see. Okay, so if you have, so one more thing I wanted to tell you for the ROC which I have left. Okay, so for the linearity property which we have, the ROC which we need to discuss. So if we have x1 of n which is having r1, okay, and x2 of n which is having r2, so then the corresponding addition of the signal x1 of n plus x2 of n, okay, so which is having the scaling factor. So the corresponding Z transform which we have seen, that is a into x1 of z plus b into x2 of z. So this actually Z, whatever Z transform ROC, okay, so this Z transform ROC will be, okay, so the intersection of these two, okay, so ROC will be intersection of these two. Okay, so if we have the ROC, separate ROC R1 for x1 signal and ROC for x2 of n signal, so then we will be having the ROC which is intersection of R1 and R2. Okay, so if we have any signal which is ROC, we have to take into consideration what exactly ROC for that particular Z transform. So if you have linearity property, it will be having R1 intersection of R2. Okay, so that is the ROC which is there for linearity property whenever you take two signals with additivity and scaling factor. So this will be the having ROC. Okay, and for the time shifting property, if you have the ROC for x of n, okay, so ROC which is having R, so even if you have a shifting of signal n minus n naught, so the ROC, so it will be remain it as same R. Okay, so whatever R it is there, the initial ROC, so that will be same. So for the shifted signal also the ROC. Okay, and even scaling domain also which is having the scaled version. So if we have the okay, so if we have the scaled version, that scaling in Z domain, if you have that alpha power n into x of n, so the corresponding Z transform we will get it as x of z by alpha. Okay, so now if you have the ROC in ROC of that x of n, the general x of n signal which will give x of z, if this is having a ROC which is having R, so then the scaling in the Z domain which will be the ROC which will be multiplied by the value alpha. So the ROC R will be changed in the Z domain, so that ROC will change with the value of alpha. Whatever alpha you will take in time domain, so in the Z domain correspondingly it will be scaled and the ROC will change from R to alpha into R. So this is about the ROCs. So that I left while discussing the property. So this you need to take care the ROC of the Z transform. Okay. So now we will go to the next one, time expansion property. Okay. So the time expansion property says that, so if we have the whatever x of n signal which is corresponding Z transform x of z, okay, so now if we have the signal that is x of xk of n, which we can represent x of the n by k. We scale the signal in time domain. Okay, so that will correspondingly we will get x of z power k. That means if we expand the signal, so as I said, x of at, whatever you have basic operation you have studied, t by a, so this will shrink the signal, okay, and this will expand the signal. Okay, so now if you use this expansion in time domain, okay, so this will increase the sample values in the z domain. So that is what we get only when the k is the integer multiples of n. Okay, k is integer multiple of n. So whenever you have the x of n by k, so you have to scale in such a way that k should be integer multiple of n. So then only you will get the proper samples in the z domain. If you don't have that integer multiples of n, then you will not be properly get the samples in the z domain. Okay, so that is what the time expansion property. So if you properly scale with the integer multiples of n in the time domain, so you will get correspondingly the z transform x of z power k. Okay, so otherwise if you have the non-integer multiples, then you will get the z transform which will be so not properly sampled. Okay, so this is about the time expansion. So even if you have if you take that summation x of z, you will be having n equal to minus infinity to plus infinity x of n into z power minus n. So now you can see here properly, if you have the k which is integer multiples of n value, so then we will get the proper sample, because these are the coefficients of z. Okay, so whatever z we will get, say for example x of 0 into z power minus that is z power 0 plus x of 1 into z power minus 1 plus like that. Whatever the coefficient value we will get only at corresponding value of n. So now if you take the scaling factor k with respect to integer multiples of n, then we will get the properly the sample coefficients, okay, in the z domain. Otherwise, so the samples will not be properly give it is in the z domain. So that is what the time expansion property. And if you properly scale it in the time domain, it will improve the efficiency in the z domain. Okay, so that is about the time expansion property. Okay, so is it understood? Any doubt? Okay, so now next one, so the next property will be the time reversal. Time reversal property, that is if x of n, which will be having the z transform x of z. So now if you have the signal which is the time is reversed, that is this is a causal signal, right? So whenever the signal which is having 0 values, when n less than 0, which we will call it as causal values. So now if you reverse this x of n with the negative values, so then you will get the z transform, corresponding z transform as x of 1 by z. So if you have the reversal of time, it will be the 1 over z value of the z transform. Okay, so we will prove this one. So x of z, we know the equation n equal to minus infinity to plus infinity x of n into z power minus n. So now we will take this x of n as, that is y of n, and corresponding y of z as x of 1 by z. That we need to prove. So now we take y of z, which is equal to n equal to minus infinity to plus infinity. So y of n into z power minus n. So now substitute y of n as the time reversed signal, that is x of minus n. So we will get it as n equal to minus infinity to plus infinity x of minus n, okay, into z power minus n. So now for this one, take something like n equal to minus n equal to plus l, or l equal to minus n. So we will get it as the y of z, which is nothing but So now whenever n equal to in minus infinity, so that L will become plus infinity, and here it will give minus infinity, and x of minus n will get it as x of plus L, and z power, so whatever minus n we are taking it as the plus L. Okay, so now we can write this one as L equal to, so even it is varying from minus infinity to plus infinity, x of L into z power minus 1 power minus L. So now we can write like this, and L is the dummy variable, you can replace it as L equal to, again L equal to n, so we will give n equal to minus infinity to plus infinity, x of n, z power minus 1 into minus z power minus 1 power minus L. So now we replace z by 1 over z, so that will give, so the value of the z transform as x of 1 by z. So you will get y of z as the z transform, which is x of 1 by z. Now if you reverse the time, okay, if you reverse the signal in time domain, so that will give correspondingly, so in the z transform x of 1 by z. Okay, so this is the time reversal property and the proof. Okay, okay, is it understood? Fine. So now this is the time reversal property, and we will move on to the next one, that is convolution property. So this is already known property in Fourier representations also. So now if we have x of n, so corresponding z transform x of z, okay, and corresponding if you have another signal y of n which is having z transform y of z. So now the convolution of x of n, so I will take it as something like v of n, which is equal to convolution of x of n into y of n. So now the corresponding z transform v of z, which is nothing but the multiplication of two signal in z domain. Okay, so if you have the convolution in time domain, so that is corresponding multiplication in the z domain. So now we will prove that. So we will take v of z, so the z transform of the signal v of n varies from minus infinity to plus infinity, v of n into z power minus n. So now substitute v of n, so the convolution of x of n and y of n, okay, so that will give minus n equal to minus infinity to plus infinity, x of n convolution y of n, okay, into z power minus n. So now we know the equation for the convolution x of n and y of n, so that you replace. So n equal to minus infinity to plus infinity summation k equal to minus infinity to plus infinity x of k into y of n minus k. So now this is the convolution which we got. So this you multiplied by the signal z power minus n. Okay, so now we will get the v of z, so which is nothing but, so now we interchange the summation, so we will get k equal to minus infinity to plus infinity x of k, and summation n equal to minus infinity to plus infinity y of n minus k into z power minus n. Okay, so now replace n minus k by the value L. Okay, so now if you replace n minus k by the value L, so you will get it as, okay, so we can write in a new page. Okay, so v of z, which we can represent as summation, so k equal to minus infinity to plus infinity x of k, and also the summation which is n equal to minus infinity to plus infinity y of n minus k into z power minus n. So this is what we have. So now replace L, which is nothing but n minus k. So whenever n is minus infinity, L also will go to minus infinity, and we can rewrite the expression as k equal to minus infinity to plus infinity x of k into, so now we can write this one as L equal to minus infinity to plus infinity. So we can replace n minus k as L, and z power minus So n we can replace it as L plus k. Okay. So now we can take this z power minus k and put it here. So you will get it as k equal to minus infinity to plus infinity x of k into z power minus k, and also the summation L equal to minus infinity to plus infinity y of L into z power minus L. So now this we can write it as, so since k and L are the dummy variables, you can replace it again by n. So what you will get? So you will get v of z as, so this we can write it as the x of z, and this we can write it as y of z. So that will give x of z into y of z. So that is what the proof for convolution property. That is, if we have the convolution in time domain, that is discrete domain, x of n convolution y of n, then it will give correspondingly the multiplication in the z domain, that is x of z into y of z. So this is about the convolution property. Okay, understood? Any doubt in this? Hello? Any doubt, anybody? Hello? Understood the properties? Sonia? Understood, Sonia? Hello? Subramanya? Any doubt? Any property? Okay. So again here ROC, whatever we discussed for the convolution property. Okay, so the ROC will be, so if we having x of n which is having ROC R1 and y of n which is having ROC R2, so then the Z transform, the ROC will be intersection of these two, R1 intersection of R2. So in the Z transform which will give the intersection of these two ROCs. Okay, so that is x1 of n signal corresponding x of z, if you take ROC as R1, and if you take corresponding y of z which is having ROC2 R2, so then the convolution which gives the multiplication into signal in z domain, that resultant ROC will be the intersection of R1 and R2. Okay, so this is about the convolution property. So now we will go to the next one, that is differentiation in z domain. Differentiation in z domain. So what is meant by differentiation in z domain? So that will be, if you have the signal which is having the x of n which is having the z transform which is gives x of z, and if you scale the factor x of n by the value n, so this will give the z transform which is having z into, so d x of z divided by dz. So this will be actually the differentiation of the x of z. So that is nothing but differentiation in z domain. So if you differentiate in z domain, so that will give the multiplication of the scaling factor n. Okay, so that we will see how we will get the differentiation property, and we will prove that. So now if we have the z of x of n, okay, so that will be considered as x of z, so which is nothing but summation n equal to minus infinity to plus infinity x of n into z power minus n. So now we know x of z, so now differentiate both the sides. So you will get dx of z divided by dz. So I am differentiating both sides x of z, and also I am differentiating here d by dz of whole expression, that is n equal to minus infinity to plus infinity x of n into z power minus n. So now since we are differentiating with respect to z, so wherever the z parameter is there, we have to apply the differentiation. So what you will get? You will get dx of z divided by dz, so which will give summation n equal to minus infinity to plus infinity x of n into d by dz of z power minus n. So what it will give? It will give n equal to minus infinity to plus infinity x of n into, so this will give minus n, okay, into z power minus n. So this is minus n, no? So minus n into z power minus n minus 1. Okay, so this will give the differentiation, and you will get, so now rewrite this expression. You will get minus, so this z power minus 1 I will take it outside. So this we can write it as, okay, so this we can write it as z power minus n and z power minus 1. So if you write this one, this minus I will take outside, and this one I will take it outside, that is z power minus 1, and remaining expression I will write, that is n equal to minus infinity to plus infinity x of n into z power minus n. So now you can carefully observe here, okay. So this complete expression we can write it as z transform of n into x of n. Can we write like that? Because n into x of n, which is there in the place of x of n, okay, and this will be replaced it as, so the x of n, treat this n into x of n as x of n, okay. So x of n into z power minus n, so on this summation we can write this as a z transform of n into x of n, okay. So now what we will get? So the z transform of x of, that is n into x of n, okay. So the z transform of n into x of n, whatever we have here, so that will give, so if you send this one this side, it will give minus z into, so this inverse if you send it to this side, you will get z, and whatever in the left hand side we have dx of z by dz. So this is what the proof for the differentiation in z domain. That is, if you have the differentiation in z domain, so that will be the scaling factor, the corresponding multiplication value n in the time domain. Okay, so this is what the differentiation in z domain. Okay, so is it understood? Any doubt? Okay, so now another one important one, it is having and here also the ROC will be same for both. If you take the x of n and x of z, here it is having ROC r, so then corresponding if you differentiate also, the ROC will remain same. ROC will remain same in this property. Okay, so now you can take another one, that is conjugation property. That is, we can take complex conjugate of the signal x of n, what will happen in the z domain. Okay, so now if we have x of n, the corresponding z transform x of z, so now if you take the complex conjugate of x of n, so now what is the corresponding, the z transform. Okay, so that is the conjugation theorem. So you will get it as x of z, x star of z star, because here, so this expression, whatever x of z expression you can write here, that is n equal to minus infinity to plus infinity x of n into z power minus n, right? So now since we are taking x of n also the complex conjugate, and z also it is having a complex value which we have to take the complex conjugate, so that's why it is represented as x star of z star. Okay, so if you have the conjugation property like this, so if you have x of n signal corresponding z transform x of z, and if you take the complex conjugate in the time domain x star of n, so the corresponding you can represent the complex conjugate of x star of z star. Now here, so if you have the x of n which is corresponding x of z, which is having the pole at the value of z. Okay, so the say for example at z equal to z naught you will be having pole. So now if you take the complex conjugate, so that will give the pole at z star value. That is, if you take the complex conjugate, so if you having the pole which is at z equal to z naught, and if you take the complex conjugate, so then it will give the pole which shift at the complex value, that is conjugate value, that is z equal to z naught star. Okay, so that will be the conjugation property. Okay, so is it understood? Any doubt in this? Okay, so another two properties are there, initial value theorem and final value theorem. So that we will discuss in the next class because it requires some time. Okay, so those two properties we will discuss in the next class. Okay, so any doubt in this? Anybody? Hello? Anybody is having any doubt? Okay, we'll